Uh, so I'll say that we get started so we don't go too much over time. So good morning, everybody. So this is day 3. I hope now you got a hang of what we are doing. So today we're going to start discussing something a bit more advanced. All right. So far we did we introduced what is density functional theory. So first, using a heuristic approach, very simple, trying to discuss which pieces one can put in, what are the approximations, and then we did a more formal introduction using the Holmberg and Cohen theorems. So all of that was to calculate a property which is called the total energy of the electrons. Okay, so that was the key. And yesterday, during the tutorials, you have seen that you can calculate that using software, and then you get this number. Certain things can be done. So today I'd like to discuss how people use that to determine equilibrium structures, which is what we've been doing yesterday. But now we're going to explain why we were doing what we were doing yesterday. So this first lecture is on finding equilibrium structures. The second one this morning is going to be one level up, and that's basically perturbing equilibrium structures, and that means studying small deformation and therefore elasticity. Okay, so this is going to be equilibrium structures. The next lecture is going to be elastic constants. I think most people will be interested in equilibrium structures because if you have something if you want to study anything using DFT, even if you have the experimental structure, you need to find what DFT thinks is the equilibrium structure. So you need to optimize it. Otherwise, you will work with something which is not the minimum from the point of view of theory. And elasticity is something more specialized. But more and more people use that, so we will discuss it just to have a feel of what one can do with these total energies. So for equilibrium, I guess yesterday you already had an idea of what one has to do. In practice, what we do is to try to build something which is called a potential energy surface, which depends on some nuclear coordinates. So from now on, we call them ionic coordinates to distinguish pseudo-potential, which is for an ion, okay, from the nucleus. So that's why sometimes you see, I will talk about nuclei when I really talk about the physical particle. When we talk about ions, it's because we are assuming that the core electrons have been already embedded in the nucleus, and therefore it's no longer the original nucleus is a new thing, which is an ion. So the ionic coordinates are basically just either the positions in the unit cell or the lattice parameters, okay? So in an external reference frame, the lattice parameters decide the lattice vectors, and therefore they decide where the positions of the ions will be when you repeat the lattice. So yesterday what we did is basically to keep the atoms in the Wyckoff sites and modify, in the case of silicon and diamond and graphite, modify the lattice parameters. Okay, so that's one particular case of a structural optimization problem. In principle, if you have a solid with let's say 1,000 atoms, so 3,000 Cartesian coordinates, well, you need to optimize all of these degrees of freedom. So as simple as that. Okay. So yesterday we've seen a case where we optimized the chlorine bond length, so one degree of freedom, the silicon lattice parameter, and 1 degree of freedom. In the case of graphite, for those of you who got there, it was the A lattice parameter and the C axis parameter, so it's 2 degrees of freedom. In the general case, so when you're looking at something which is not extremely well understood from experiment or with a complex crystal structure, you may have very many degrees of freedom. So one has to understand exactly what needs to be done and also find automated procedures for doing these searches. You cannot calculate total energies for many degrees of freedom if you have like already for graphite. You've seen there are many calculations. For each A lattice parameters, you will need to do a calculation for every other C lattice parameter. So if you have 20 of those, it's going to be a lot of calculations, okay? So now we're going to see some techniques that people use to avoid doing explicit calculations. But before getting there, I would like to explain why we were looking at the total energy yesterday in the tutorial. That's a bit intuitive. So we started with the assumption that you look at the minimum total energy and that's your answer. But the question is why that is the case. And there is a very rigorous answer to this question. So the answer actually requires us to step back in what we were discussing in terms of theory. So you remember we started from something we call the clamped nuclei approximation. So when we had the many-body Schrödinger equation, there were electrons, nuclei, everything. Okay. Then we said this is too difficult. Nuclei are very heavy, so we can actually drop the kinetic energy of the nuclei and drop their nucleus-nuclear interaction. So we were left with an equation only for the electrons, where the nuclear position were kept fixed. Okay, that was the clumped nuclear approximation. So if you want to study, what happens, so how things depend on the nuclear positions, well, you need to get rid of this approximation, because in this approximation we don't see nuclei anymore. Okay, they are just fixed charges somewhere. So we need to get rid of that, and essentially what we need to do is to go back to this equation. That would be the one that we called the elephant a couple of days ago. So it's the many-body Schrödinger equation for electrons and for nuclei. And here you see there are no coefficients, basically no numerical coefficient. That's in R3 units. So we already used the clean units. And importantly here, the wave function, the many-body wave function, is not only a function of the electronic coordinates, but also the nuclear coordinates. So when you have a quantum system, electrons and nuclei, the wave function describes everything. All right? So that's basically the complication. So far, we only focused on the case of electrons. So now we need to understand how to go from this object to find out how to use that and to combine that with the fact that in the FT we can calculate total energies of electrons when the nuclei are fixed. Okay, so we have some piece of information from the FT. We have that, so we need to try to put them together. So the connecting point is something that I like to explain with an example. So this is actually a very simple calculation. So this, what you see here, so basically on the right, it's a plot of what is of this equation basically. So this is a Schrödinger equation in one dimension. Okay, so the second derivative of a wave function, and that's a kinetic energy, 1 divided twice the mass, plus potential energy times psi equal eigenvalue times psi. So what I'm doing here is to just make up a potential energy that I like. Okay, it's an example. So this is a potential well, which is a parabola, and is represented by this black line here. Okay, so I'm basically saying I would like to solve a simple one-dimensional quantum mechanical problem where the potential is a parabola. And just for the sake of to make things which are not too far from reality, I've chosen this proportionality constant here using basically the strength of the carbon-carbon bond in diamond. Okay, so just to have a number which makes a little bit of sense. Then what you see here, that once you decide this potential, okay, well, you need to find the solutions, so wave functions and eigenvalues. And what I want to study now is only the lowest energy eigenvalue, so the ground state. Okay, so what is interesting is that there is one parameter left, which is the mass. All right, so I can make various choices for the mass. I'm not specifying what that is. And what I want to compare in this picture is two situations. One, I choose the mass to be the electron mass. So in this equation, that becomes 1, okay, in, let's say, R3 units. And that gives me basically a wave function, which is the red line. Okay. So the second situation is that I set the mass, as an example, to lead. Okay. So now, let me just see the, no, it's not this one, it's this one. So if I look at the periodic table, so lead, the mass is about 200, okay. So it's here. It's about 200, let's say, atomic mass units. So it's like proton masses, let's say, and that's 2,000 times an electron mass. So that's a very, very large number here. Okay. So if I solve the same equation using the lead mass, I get this wave function. So clearly, this is something you've seen a lot of times, during your undergrad courses. This is basically a parabolic potential is the quantum harmonic oscillator, and the ground state wave function is a Gaussian. So the only difference between the red line and the blue line is that there are two Gaussians, but one has a much broader width. Okay. So the key point in this story is that if you imagine this to be the interaction between electrons and nuclei, because the interaction is a reciprocal thing. So an electron sees the same force that the nucleus sees from the electron. Okay. So if you keep the interaction, but you solve the equation for two cases, the mass of the electron, the mass of the nucleus, the wave function will look dramatically different. All right. So that's actually what distinguishes nuclei and electrons from the point of view of in quantum mechanics. So the main observation we want to make now, so that's step number 1, is that if you look at the probability density you find in the lead nucleus here, well, it's pretty much always at this point, all right? So it's not going to be all over the place. So that's just one approximation, which is maybe if I want to study a couple system like that, so the electrons and nuclear wave functions, I don't need to really consider probability of finding the nucleus everywhere. But I can actually imagine that I can calculate the electron wave functions with the nuclei more or less at this point, okay, without bothering too much doing complicated things. So this actually is what Born and Oppenheimer proposed in 1927, okay? So you have to imagine that so that was published in 1927. That means it was probably submitted, maybe 10 months earlier. So they wrote this thing maybe a couple of months after they seen for the first time the Schrödinger equation published, okay? So that was already quite advanced, the level at which they were thinking about these, problems with several atoms. And this approximation is quite, is basically the key to everything that we do today in terms of structural optimization. So the idea that they had is the following. Instead of studying a wave function which depends on all the variables, and for every possibility of the nuclear variables, we try to study what happens for the electron variables. We looked for a product form, okay, a wave function which only depends on the electronic coordinates, and which actually has the ionic coordinate parametrically built in. That means I try to look for a wave function for a lot of sets of nuclear coordinates. And then I make the product of that with a wave function which depends only on the nuclear coordinates, okay? So this is called the Born-Oppenheimer approximation. So this is not exact. This is an ansatz. It's basically, it's the answer to the question, I don't know what to do, how do I proceed? So that's actually a possible way to proceed. So this is actually, again, one approximation, and it has several names. So when people talk about the adiabatic approximation, that is it, all right? If you include further terms, so that you can imagine this being the lowest term of an expansion, if you include further terms, what you obtain there is things called electron-phonon interactions, for instance. We will not do that in this lecture course. So for now, we just look at the ground state, and we stay with this adiabatic approximation. So again, this is an ansatz, and the question is, if you use that in the previous equations, what does happen? So the first observation is that you want to do that because what we've done until now is to discuss solutions of the Schrödinger equation if you freeze the nuclei and look only at the electrons, okay? So if you think about it, during yesterday and Monday, so we basically introduced the notion that DFT is a way to solve the many electron problem when nuclei are fixed, okay? So we know how to solve that in the sense that we understood what it is. There are theorems. There is software. We understand what happens there. So let's say the electronic problem is well defined and it can be solved. This was the many-body electronic Schrödinger equation. And what we discussed is that very complicated, but the total energy can be calculated using DFT. So we can replace all these monsters, all these wave functions, using single particle equations and all that, and basically obtain this number using DFT. So that's the number you get at the end of the calculation, okay, during the tutorials. So the electronic problem is solved. So at this point, what people do is something very simple. They combine this equation, okay, with this ansatz together with this equation, all right? So the steps are in the book, and really it takes maybe a couple of minutes. It is a bit boring, but it's very easy. So if you combine this, and that, actually what happens is basically that the electronic wave function drops out, and you are left with an equation where only the nuclear wave function remains here and here, okay? So it's an equation now where you have the nuclear kinetic energy, the internuclear repulsion, okay? And then there is this object. This object is the total energy of the electrons when the nuclei are in certain positions. So this actually is something which is quite spectacular, and the first time I learned about that, I was very fascinated because in practice we start from an equation where everything is coupled. This is a big Schrödinger equation. Then you use these ansatz, and what happens is that you factor out the problem into an electronic problem that we learn how to solve in DFT. And then there is a nuclear problem, which is this one. So the interesting bit is that in this equation, the kinetic energy is what we expect to be, like just the quantum kinetic energy, is p squared over twice the mass. Then there is a repulsion energy, which is obviously there because the nuclei are charged, so they repel each other. But there is an extra term, which is surprising, and it is basically the total energy of the electrons for the nuclei in a certain configuration. So this is actually quite interesting because it means that since this depends only on the position variables, not on the derivatives, that what you can think of is a situation where the nuclear wave functions obey an equation which now has a kinetic energy part and a potential energy. And the potential energy contains two contributions. So one contribution has to come from the repulsion, and one has to come from the total energy of the electrons. So this is not obvious, okay? So I would not have guessed that you have the total energy of the electrons appearing as a potential on the nuclear coordinates. So this object here is what people call the potential energy surface, okay? So if you go to quantum chemistry, you study reactions and things like that, people talk a lot about potential energy surfaces. So that is the formal definition. It's basically the repulsion between nuclei and then this term. So what this term means is basically that you have a situation where the nuclei are, want to be further apart from each other, and the electrons actually are acting as a glue to keep everything together, okay? So and this quantity is what we obtain from the FT, okay? So this is something which is calculated by hand. So like you put the atomic number here, divide by the distance between nuclei. You don't need any calculations. It's just a number, okay? So in practice, what happens is that this is the quantity that we see at the end of the code. And now there is a little cheat. So so far what we looked at in the code is a total energy, okay? And I didn't tell you so far that total energy was not the energy of electrons, without nuclei. That number was actually the whole of it, okay? So in fact, in that number, so if you look at the lines where there is a partition of various energies at the end of the output, you will see that there is a term called the Ewald term. So Ewald. So the Ewald term is precisely this thing, okay? It's called Ewald term because you can imagine that if you have an infinite crystal, adding up Coulomb interactions for an infinite crystal may lead to an infinity, basically an infinity. You may not converge. So there is a technique to perform this sum, which is called Ewald summation. So actually, this is something that in principle you should know because it's one of the first appendices of the book by Kittel. Okay, so this is the same. The Ewald summation is the same that is used to calculate the Madelung energies of ionic crystals, so by hand, so without DFT. Okay, so that's exactly the same strategy. It's something which has been known, way, before the birth of DFT. But basically, the bottom line is that yesterday I've been calculating actually this number, basically total energy including electronic energy and repulsion between nuclei. And that's what we call the potential energy surface, okay? So why this now is useful and how do we understand it? So let me make an example. So this is something that I put there because I find it quite, so it's so simple and it contains most of the physics that we need to know. So that's an exercise. I think it's 4.4 in the book. I just did by hand. I mean, it's something that is probably the only case where you can do something like that by hand in maybe half an hour, 20 minutes. So it is essentially the simplest molecular system. Okay. So the simplest molecular system, what you can guess that well, it has to have more than one atom, otherwise it's not a molecule. And you want this to be the smallest possible number of atoms, so you choose 2. Then you want the simplest atoms, so you go for hydrogen. Okay. So the simplest molecule in principle would be H2, right? Now that's already too complicated because there are 2 electrons. So you can do a calculation using the FT, but I wanted to do something by hand, and you cannot do solutions by hand for 2 electrons. So what I did is I considered the H2 plus. That's what the hydronium is. Hydronium radical is basically H2 plus. So it's the H2 molecule, but you strip off 1 electron. So that object exists in nature. So the reason for stripping off an electron is that if you're left with only 1 electron and 2 nuclei, it's not a many-body problem. It's the problem of 1 single electron in the potential given by 2 nuclei. So that's we go back to undergrad quantum mechanics. You need to solve that problem of quantum mechanics, okay? So at this point, you can try and calculate basically the repulsion between the nuclei. So that would be this term. And that would be the proton charge, so E and E, divided by their distance, okay? So it would be the 1 square, because we are in atomic units, divided by the distance. So this is this term, so 1 over distance, okay? So then there is another bit, which has to be the total energy of the electrons in a given, for the nuclei at a given distance. So essentially is the lowest energy eigenvalue of this electron. So that, in principle, is something a bit complicated because you have a strange topology. 2 nuclear potential is not a nice quantum well, it's not too easy. But actually, it's not too difficult to do because what you can do is to place the protons here and then use what is called the, when you use a tight binding approximation, you put 1 electron in the 1s here, 1 in the 1s here. Basically, when you make this approach, the 2 1s levels, they form basically the split. You have a bonding state, anti-bonding state. This can be calculated. You find it in any textbook, like the first approach, to the simplest problem that people do in quantum chemistry. Basically, you can calculate this value, knowing the distance between the protons, okay? And that can be done by hand. There is an analytic expression, so you find it in the book. So you can really write down an analytic expression for this total energy, and that's the red line. So if you add them up, what you obtain is this black line, which is basically this object, right? The potential energy surface, Coulomb plus total energy of the electrons. So it's this plus that. It gives this black line. So what is interesting, so the reason why I like this example, so here there is no DFT, there is no numerics, it's really done all by hand. In the book you will find the analytic expression for that. The interesting bit is that the shape of the potential well, if you remember the tutorials from yesterday, is exactly the same that you find in chlorine. I mean, apart from details, but the qualitative shape is the same. It's the same you find in silicon. It's the same you find in diamond. It's the same you find in graphite. So it cannot be a coincidence. So actually, some people found in the past that there is actually a general law, which is called the universal binding energy curve, which describes pretty much every system near equilibrium. So everything from molecules to solids will have some kind of a potential well like that. Okay. So from that you can tell, for instance, the equilibrium geometry of this molecule. You can tell the binding energy with respect to like dissociation, and you can do many other things. So what we have been doing yesterday is essentially trying to calculate this curve, not from the simple system, but for more complicated systems. Okay, but the physics is entirely contained in this expression, and that comes from the Born-Oppenheimer approximation, where we separate the nuclear and the electronics degrees of freedom. So that's one bit of information. So now I want to go back to this picture of these two-wave functions, nucleus and electrons. I want to basically use this information for making another step. So what we just said before is that from that we can tell the nuclei are pretty much always near the same position, so we can maybe think of solve the problem for electrons for nuclei at a given point instead of letting them move around in a wave function. There is another piece of information that you can see from this plot. So if you actually use a bit of imagination, so this looks really like a Dirac delta function, right? So a very spiked function. And to me, when I look at that, the first thing that comes to mind is that maybe, so when I think about a wave function, I think about something broad and like a cloud of things where you can find the particle anywhere. Okay, but if you look at this wave function, to me it looks like more than a wave function. It looks like a particle, like a classical particle at a given point, because the probability of finding it there is very large. The probability of finding anywhere else is very small. So I could almost say that this particle is not really a quantum particle because it's so localized here that it does not really have a wave function in any meaningful way. Okay, so this statement is not entirely true because there are things called quantum nuclear effects. For instance, they are important when you study XRD. So the Debye-Waller factor basically takes into account. So that, when you do XRD, did you see XRD spectra? Yes. So the ellipsoids, like the thermal ellipsoids, well, they basically reflect the width of this function. Okay, but clearly, apart from the ellipsoids, you know that there is a particle at the center of the ellipsoid. So you can actually forget about that and actually write down the Wyckoff size, right? So that's what you record, and what you give to someone is the Wyckoff size. So if we do the same operation, we forget the wave function, we only keep the Wyckoff size, what we can say is that instead of using a quantum Schrödinger equation for the nuclei, so that's what we had before, right? Let me go back a second. So this was the Schrödinger equation for nuclei, the kinetic energy plus the potential energy. So instead of using the quantum Schrödinger equation, if particles have a very, very narrow wave function, they are almost localized at a point, well, then what we could do is to get rid of quantum mechanics and treat nuclei using classical mechanics, right? So what people do at this point is the opposite of what we do in undergrad courses, where you say, oh, I know classical mechanics, and I have the momentum, I replace that with the quantum momentum, and I will take quantum mechanics. So here we are going the other way around. We are saying we have a quantum mechanical equation, Schrödinger equation for the nuclei. I making the observation that the wave function is so narrow that it's basically like a point particle is describing at a given point. So instead of having to work with a very complex mathematical formalism, people say, okay, let's get rid of quantum mechanics and replace the quantum momentum by the classical momentum. Okay? So basically, I make a classical approximation for the nuclei. So this approximation is extremely common today. That's what we've been using yesterday in the tutorials. That is used in, I would say, maybe, I don't know, this is just a very brutal guess, but maybe 90% of modern calculations use this approximation, okay? So there is a part of the community, the electronic structure community, which actually is trying to look for very, very fine effect, which come when you go back and you actually include the quantum fluctuations of the nuclei. But that's essentially is a small portion of the community. In practice, when you do these operations, you kind of kill all zero-point effect, and that's actually the main price that you pay. But for a first characterization of a system, zero-point effect typically are quite small, so you don't need to worry too much. Okay. So when you do that now, basically we have a Hamiltonian. So basically we have a Hamiltonian which looks like momentum squared divided twice the mass plus a potential energy. So what is the set of dynamical equations which describes time evolution of a particle under this Hamiltonian? Well, you have it in the notes, but you should know that. So whenever you have a classical Hamiltonian, okay, the law of motion basically is simply the Newton's equation. All right. So what you can say basically is that the change basically of momentum with time is the minus the derivative of the potential energy with respect to the coordinate of the particle. Okay? So that's a standard result which has nothing to do with quantum mechanics, which has nothing to do with DFT. It's something which has to do with like classical mechanics from like high school. Okay? So I'm not inventing anything here. So I'm just saying that when you have a standard classical kinetic energy and a potential energy, basically the law of motion is given by the Newton's equation. So one can rewrite that as a force equal mass times acceleration. That's all identical. So that means that when you do this replacement, quantum to classical, you end up with a situation where you can find out Newton's equations for the nuclei, okay? And the good news is that the force on each nucleus is given by this bit. So the force is simply minus the derivative of the potential energy surface with respect to the coordinate of the particle. So that actually is very important. Why? Because now this gives us essentially a tool to study forces on nuclei by calculating this quantity. And we said that quantity is the total energy in DFT plus the Coulomb repulsion between nuclei. So that's basically what we have available at the very end of a calculation in the codes. Okay? So that number, if you take the derivative, so for example, by finite difference with respect to the nuclear position, you will find the force which is acting on that nucleus. So what we will see today is a situation in the tutorial, it's a situation where we're going to start from a chlorine atom. Instead of consider equilibrium, we're going to place them like 3 angstroms apart or 4 angstroms apart, and you're just going to look at the forces, and you will see there will be huge forces towards each other, which means I want to go back to equilibrium. And that is calculated precisely using this expression. Okay? So the move from quantum mechanics for nuclei to classical mechanics allows us to define very easily forces. And that's actually something very useful. At this point, you can guess that if you have the forces, okay, you may start thinking about, suppose you start from a structure which is very far from equilibrium. So how can you find the equilibrium structure? What you could do is to calculate the forces and basically move atoms according to the direction of the forces until basically forces are 0. So that's precisely what people do to find equilibrium structures. So that's what we will do today in the tutorial session. So just to make a last statement about that is that, one last statement is that, so this equation is precisely what is used in what is called ab initio molecular dynamics, okay? So when people move, so you see, I don't know, movies of, atoms moving around and they tell you that it's done with DFT and things like that, most likely it has been done using this equation. So they calculate at each time step the potential energy. From that, they obtain the forces, and from the forces, then they move the atoms. Okay, so that's what is a ab initio molecular dynamics calculation. So there are some subtleties, there are some technical problems, but I will not discuss them here. So what I want to just mention is a way to use these forces in order to find equilibrium structures. So in practice, you can imagine the following situation. Suppose you have the potential energy and a certain coordinate, and we say that the potential, the equilibrium is defined by this point, and the particle can be anywhere here. So that's like for chlorine. So imagine that we start from this point, okay? So this is actually is not a particle, it's a fictitious parameter, okay? Just a way to keep in mind that we are at this bond length. So if we start at this bond length, and we use this equation, okay? So the force is the slope of the, sorry, can you see me? The force is the slope of that. So clearly in this case, the particle wants to go this way, okay, towards the minimum. So if you start solving this equation numerically, what you will find is basically the oscillation of this object around this minimum. And since there is no dissipation, so the problem is conservative. So you will have this going back and forth, maintaining the height because the energy is conserved. So if you do that, basically you keep oscillating. But if you think about it, suppose I put a bit of friction. Suppose this particle is moving in a fluid, okay? What is going to happen is that this is going to lose energy to the fluid, so it will be doing this. At some point, it reaches the minimum. So in this case, it's trivial because we see the minimum. Okay, why do we do that? But imagine a situation where you have 1,000 atoms and the potential energy surface which has 3,000, so 3 times 1,000 degrees of freedom. So trying to find the minimum is it's quite a disaster. So it's one of the most difficult problems that exists today, because you have a very basically potential energy surface with very, very many degrees of freedom, and it's not going to look like that. It's going to maybe look something like. So if you do something like that, you may end up here, but that's not the global minimum. You would like to be here. So that's a very, very big problem. Okay. But anyway, the point is that this technique, so trying to dump the energy of the particles to find the minimum, is something which is used today. So to give you an idea, what people do, and that's only 1D, but in practice this is done for every coordinate in the system, they write down the Newton's equation, like second derivative of the position with respect to time, is basically the acceleration. Then this is the force, where u is calculated from dft, and then you add a little friction term which is proportional to the velocity. Okay, so this is exactly the same that people study in physics 101. There's nothing different. The only difference is that instead of having a potential given as an analytic form, like, oh, this is the exercise, this is the potential, here this object is being calculated using dft. If you do that, suppose that you start from a position at this point and the particle is moving around a minimum here, by dumping, essentially you start going through some fluctuation. At some point, you find the equilibrium coordinates. Okay, so that's what I was saying here. So this is just an example in 1D, and it's again an analytical expression. So how do people would people do that numerically? So what they do in practice, I'll go on this side. So what they do, that's the simplest possible way, and is not the best way. Okay, but it's easy to understand. So what you can do is to just write this second derivative using finite differences. Okay. So if you use symmetric finite differences, basically it's the position at time, let's say I plus 1, minus twice the position at time I plus the position at time I minus 1. So that's basically, if you divide by delta t squared, where delta t is the time interval, that's an approximation for the second derivative. Similarly, you can have the partial derivative with respect to position by taking the value of the potential energy here minus the value at this other time point, and then you have this difference below. And similarly, you can do the first derivative in the same way. So the reason why I'm showing you that is that here, the position at time I and I minus 1, okay, they are known if you are already if you want to look at what happens at the next time. So this is known, so it can be calculated. This can be calculated. This is known. This is known. Parameters. This is known. This is known. So in practice, this is an expression where the only unknown would be the position of the nucleus at time I plus 1. Okay. So if you rewrite this in such a way that it becomes an explicit expression for x I plus 1, whenever you know the position of the previous two times and the values of the potential energy surface, you can basically propagate and find the next position. Okay? So this algorithm is not something that I made up. It's called the Verlet algorithm, and this is what is used in something called damped molecular dynamics. Okay? So this is also something that you can use as an option in quantum espresso, and it's something that works quite well. So today, this is not the most common way of doing it. Typically, you can do that if you have a solid with very few symmetries, where the situation is very difficult and you know what to do. But for crystals where you already have a guess of what the structure is, people now use something called conjugate gradient methods, which are basically some linear algebra techniques to minimize, in a big linear space, let's say. So this is nothing to do again with the DFT. It's basically the problem of having a function of many parameters, and you want to find the minimum. So it's an optimization problem, which again, for which people develop techniques regardless of DFT. Okay, so the techniques in fact were borrowed by other fields, not from they didn't come from DFT directly. All right. So that's basically to say what more or less what we are doing if we are trying to find equilibrium structures, and yeah.
You had a choice on the right-hand side of your finite differences. You could have written this equation with just I and I minus 1 on the right-hand side. Why did you put I plus 1?
Oh, that's that changes slightly the accuracy of the equation. I mean,
Okay,
so yeah, basically symmetric difference is one order higher in basically. So the error is delta t squared as opposed to delta t.
Okay.
So that gives an implicit method, in fact. So that depends again on that.
Yeah.
What you're talking about is an explicit method, which is typically slightly less stable. But I mean, this is just an example. There are many, many ways. There are things which are even much more complex. You can express derivatives with using, a chain of values. So you can use higher order expressions. So bottom line. So we will do that, and then I will give you 2-3 examples quickly. So what happens in a DFT code, okay, in the most general case, is the following. You decide where the nuclei are, and that's what you've seen yesterday. You place the atoms at certain positions, okay? At this point, the code wants to calculate the total energy in DFT, so electron density and total energy. So this is the DFT step. You remember yesterday I gave you a flow chart, okay, for DFT, iterations, exchange correlation, all these things. The whole flow chart is here, okay, inside this bit. So once one has the total energy, one can get the potential energy surface by adding the nuclear repulsion, and then you can evaluate the forces using this expression. Once you have the forces, you can update the atomic positions if you want to find the equilibrium structures. Okay? If the new positions are now equal to the old positions, you exit, and if they are different, you keep looping around, and basically you say, okay, calculate again total energy, forces, move atoms, and so on. So basically that's an outer loop which contains the DFT loop. We have not seen that yesterday. We will do it today, basically. So today, what we will try, so yesterday what we did is to calculate minima, for instance, of chlorine by mapping this function and looking at the minimum. Today, we will start from chlorine at a very large separation, and we try to let the chlorine molecule find its minimum using this kind of procedure. That's basically the most common procedure in practice, unless you have extremely symmetric systems, okay? So if you have many atoms, that's what people do. A couple of examples. So that's something that we did already yesterday, so it should be familiar. And it's probably just a way to to introduce this to those who did not arrive to this point yesterday. So if you try to do this operation for, yesterday with the chlorine molecule, this is an example that you find in the book about the nitrogen molecule, just another molecule. What you should find is that the potential energy surface is given by these black points, okay? So you find a minimum here, so you have a bond length here, and you have a binding energy. If you zoom in this expression, that's what we did in the tutorial, you will find, basically, you will be able to define a binding energy and equilibrium bond length. I'm showing this because I want, again, to give you a comparison with the experiment. So this is DFT-LDA. So the bond length is 1.102, and the experiment is 1.098, so the error is 0.4% in this case, okay? So that's very good, again. And if you look at the binding energy instead, DFT-LDA is 11.46, and the experiment is 9.76. So again, is in this case, it may be 1.5 volts too large, which is about 17%. So that's very typical. So we've seen chlorine, it was a similar result. Silicon, it was a similar result. So that's always the case. And that's specific to the LDA. As I told you, in other functionals, this can get better. Now, I just want to make a point here. I don't know, let me show. So did you notice that? So this is the binding energy. That should be the total energy of the molecule minus twice the energy of the atoms. Okay? So what you expect is that when you go, that's a bit technical, but I think it's useful to say, when you go to very large separation, this number should go to 0, right? Because it's total energy of molecule at a certain distance minus twice the energy of the atoms. If the molecule has become 2 atoms, it has to be 0, this number. So if you look at that, it doesn't go to 0. Okay, so okay, this is wrong. It is kind of wrong, but it's not that wrong. So the number is correct. What is wrong is this limit. So this is simply a case where basically I did a calculation by taking the molecule and pulling further apart, okay? And then I compare the calculation with those of with the calculation of a nitrogen atom in isolation. Problem is that in nitrogen, we had the same problem as for chlorine. Basically, you have a P3, basically occupation. So by Hund's rule, you have up, 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 let's say. So it's a spin 3.5. So when I did the calculation on nitrogen, I used this spin configuration. But the N2 molecule is spin compensated. There are 14 electrons, so it's all basically there is no spin on the molecule. There is no net magnetization. Because of that, what I did is to, at each distance, I kept the spin compensated configuration, so there is no spin. So that means that at a large distance, even if there were like 2 separate atoms, the code was enforcing no spin. So we are comparing a situation where this has basically no spin, but the isolated atom has some spin. So clearly, the energy of that is higher because the ground state has, spin 3.5. So what that is telling us is that as you, pull a molecule apart, for instance, but that's the same for a solid, for a defect, for anything, you start from a configuration without any spin, but you may end up with a configuration where you have, spin up and spin down or something else. So at each bond length, one has to check what is the ground state spin configuration. So that's another complexity which makes things quite complicated. I haven't done this here just for simplicity, but I think this is just a warning flag to say that we cannot predict, so we cannot assume that a structure, as you pull it apart, maintains the same spin configuration. We should always look for the ground state. That means we compare several spin configurations and we pick the lowest one. Okay, so even for the nitrogen molecule, which is trivial, the situation is not that straightforward, let's say. That's just to make a point. So this is the example of silicon. And so the difference with respect to what we said yesterday is that yesterday we looked at basically silicon in the diamond structure. So it's a FCC lattice, okay? And we had got something like that, right? So also in this case, if you go to a very large, basically lattice parameter, so you see this almost hits 0 here. If you continue this curve, it's going to go above 0. That's exactly the same problem as for nitrogen because silicon will have a spin in isolation. So there is an extra plot here I would like to show you, which we have not done and we will not do. And that answers the following question. When you find the equilibrium lattice parameter, that's fine. And you find a number and you say, OK, I'm happy there is this equilibrium thing, right? Now, one could ask another question. How do you know that the diamond structure is the equilibrium one? So there are many other structures which are possible, OK? So the only way to figure that out is very simply to repeat the same operation for another structure. Like this is the beta-tin structure of silicon, which is like the standard structure, but it's a bit compressed. It's a bit like a pancake style. Okay, it's a bit flat. So if you look at the beta-tin, what you realize is that at the minimum, okay, when you find the equilibrium geometry, the energy is higher than here. Therefore, we can tell that the diamond structure is the most stable in silicon. So now I don't remember if you have, probably you have it in the exercise today. You will be asked to compare the total energy of diamond and graphite. And actually, at that point, what is interesting is that this separation is extremely tiny. We are talking about like 20 or 30 millivolts. And what is funny there is that LDA, I think, predicts that diamond is more stable, and so another functional, PBE, predicts the opposite. So that's just to mention that the prediction of the stable crystal structures is a very difficult business. I mean, when there are various competing phases nearby in energy. So there are lots of people, very good people, trying to work this out these days. And the main problem is that the energy difference are very small. So it's not that we don't have the techniques. It's that we are talking about very, very small numbers, so it's very easy to make mistakes. This is just, again, a comparison. If you compare lattice parameters, we are within 1%, and the total, the cohesive energy, which is energy of the crystal minus the atoms, is about 1 eV too large. And this is more something, okay, we are a bit over time, so I will be very fast here. It's just an example of how to do a relaxation, something a bit more interesting than just a bulk structure. So whenever you study something, that you might think of kind of publishing, typically we're talking about something which is not bulk silicon, okay? Something that requires a bit of effort. So this is an example of the already something very old, which is the surface reconstruction in silicon. So maybe around 2000, or 98, 99. So there was a lot of interest in silicon surfaces and interfaces with the oxide of silicon for electronics. So there was an interesting understanding what is the stable form of the clean silicon O1 surface. Okay, so you can try to do this by calculations. So how would you do about that? How would you go about that? What you do is to prepare a slab of silicon. So what you can see here basically is that we have the unit cell, but we repeated periodically the atoms in order to form a slab. Okay, so in the calculation we had yesterday, it was 2 atoms only in an infinite structure. So this is carving out just a slab out of that structure. So the independent atoms in these calculations are only those, in this box basically. There are 4 atoms in each plane, and then there are, I think, 11 layers here. Okay, that's just a guess. So this is a view of the periodic system, so it basically is infinite in the plane. So what you see here is that I place some hydrogens, because each silicon atom has basically 4 electrons, and if you don't place hydrogens, you would have some dangling bonds. So that's basically like a passivation step. Now, there is also passivation in DFT calculation, basically. So that's to make sure that the system is insulating and you don't have any states in the gap, which would be very odd to study. On this side, instead, we leave it like it is, because that's the structure in the experiments people started from. And one other technicality is that if you leave the system as it is and you let it relax, it will actually shrink a bit. Okay? And that's quite an interesting effect, like a rubber, because it's missing electrons here, so it's looking for electrons somewhere near the middle of the thing. So this will not be very close to actual bulk silicon on this side. So one technique people use is that they fix the lowest, let's say, 2 or 4 layers to exactly bulk silicon. So you know that the structure is converging towards something which looks exactly like a silicon crystal. And then you let all these atoms relax using these techniques, like the forces and everything. Okay? So the interesting bit is that here there is a lot of parameters, and this is very difficult to explore. Even if it looks very simple, you need to consider at least the displacements of 1, 2, 3, and 4 atoms. So there are many possible structures. So here I just want to give you an idea of what happens if you try to play around with the system. So this is the top layer, okay, that I was showing you before. And basically that's the same as in this picture here. Okay, so basically if you slice this layer here, okay, maybe I'll go, can you see me here, guys? So if you slice this bit, so you get this thing here, okay? So now these are basically bonds all vertically aligned. That's very, very unstable. If you just start the calculation with this guy slightly, asymmetric, it will all collapse. And the way it will collapse is into this structure. So basically, the reason is very simple, if you think about it. So there are very, very simple reasons for these things to happen. So here, basically, there are 2 electrons sticking out like that. Okay, that's very energetically unstable because they're all in the same orbital, and there are 4 basically electrons per each dimer. Looking at that at the same energy. So if you do something like that, so there's 2 bonds, basically they flip towards each other. So the one in the middle will form bonding anti-bonding combination. So the bonding one will be a bit lower, so it can be filled by 2 electrons. So here, this will be filled by 2 electrons. There will be 2 sticking out like that. So this is more stable because it's lower energy than that. So now basically there are 2 electrons sticking out like that. If you perturb slightly that, if you break the symmetry, you will see the system, boom, collapses to this one. So the reason for that, at this point, is the fact that you are like that. So there is 2 electrons at the same energy. If you perturb the system, the 2 energies will be basically, the degeneracy will be broken. So we have a state at low energy that can be filled by 2 electrons. So what will happen is basically that these will be filled by 2 electrons. And here we have silicon in sp3 configuration. Okay? So here there will be a state with 2 electrons left. So this is a bit more stable than this one and much more stable than this one. Now, when you're here, you're a bit stuck because you will not be able to go there. But if you restart that by nudging this down a bit and this down a bit, the second one, you actually discover that you end up in this one, which is actually the most stable. The reason why this is more stable is actually what probably you remember from undergrad courses is the Peier's distortion. So you have a bunch of electrons here lined up in a one-dimensional row. Okay, that's unstable towards dimerization. So that's why you form dimers like that. So that's what DFT says, but there is no proof that that has anything to do with the experiment, clearly. So what you have to do at this point, typically, is to try to perform some kind of spectroscopy in your system and compare it with the experiment. So here, it's a fortunate case. So I was given basically this experiment by Professor Yokoyama in Japan. So these are basically STM experiments at, I don't know, a few Kelvin or something like that. And essentially, these are the STM maps of all the reconstruction I showed you before. So this is the first one, the second, the third one, and so on. So you see, these are basically parallel rows. This shows only one row. This shows something zigzag, and the zigzag is the same on both sides. And basically, the only one which seems to be matching experiment is this one where the zigzag goes like that, okay, which is precisely this one, okay. So that's actually a very clear indication that the structure obtained here, the lowest energy structure, is precisely the one which is observed in experiment. So that's actually quite spectacular proof in the sense that it is not as easy to find such clean STM images. Typically, when people ask us to interpret some of their STM spectra, it's much more of a mess than that. So silicon is a very nice example. So I guess this is the end of this bit, and we adjourn in 20 minutes.